Say hi, too. How's it going there? I'll catch it.
Hi there. Welcome to Space Clubs. If you've never been here before, this is a public talk series run out of the National Observatory and the University of Arizona. Every month we feature a speaker on some interesting topic on astronomy. Today's speaker is Dr. Jen Andrews. Jen is an extremely close friend of mine and an excellent scientist over here, and we're privileged to have her. Jen did her PhD at LSU with Jeff Clayton and Arlo Landau, among other luminaries in the field. And she's been studying supernovae, stars that blow up. From LSU, she went over to the University of Massachusetts at Amherst, where she was a postdoc before joining. Where she was a postdoc, and now she's over here working with Nathan Smith on stars that die. And so this is some really cool research. Now, if you've never been over here before, there are a few rules for spacecrafts. The biggest one is if a train goes by, our speaker will say choo-choo, and please join her having a chug of beer at the time. If you don't have beer, please get some from your bartenders. Tip your bartenders like you would your mom. They will love you forever. There's some pizza back there, hopefully still. Unfortunately today, the projector, I believe, is missing its red channel, so things might be a little bit blue. But if you are feeling blue, you are in a bar, so have another beer. Without further ado, I will give this over to Jen, so please give us a hand for her.
Should I hold it or put it in the stand? I don't you mean hold it? Okay. All right, so as Gotham alluded to, I'm going to talk to you tonight about the deaths of massive stars. So we're going to discuss how massive stars die, and I'm really, really sad that there's no red because there's some very pretty pictures on here. So unless you are dropping psychedelic drugs, you're not going to see them tonight. But you know, if you do see them, good on you. Okay, so I was told that I needed to disperse some trivia questions throughout the talk so that you guys could get some really fancy treats. Wait, do they yell it out or do they raise their hand?
Well, ideally yell it out and raise their hand so we know roughly where to go.
Okay. All right, so we're going to, hopefully by the end of this talk, you'll understand what it takes to get this beautiful picture that we see up here. It's more beautiful on my screen, but, you know, whatever. So the first question, and Gotham's kind of already given it away, but where do all of the elements that are heavier than hydrogen and helium come from in the universe?
Supernova.
All right.
Ready? Look at that.
Supernova is correct, and so that is going to be the theme of the rest of the night. We're going to discuss supernovae, and this question should, maybe for some of you, bring to mind this very, very popular quote, and you may recognize this attractive man here in a turtleneck. And the quote is, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. So this is a very deep quote, but it's true. Everything from hydrogen to helium, everything that we know, love, own, comes from the interiors of massive stars. Well, they come from other supernovae. So this is where we're going to take a little aside and discuss there are two types of supernovae. We are going to be discussing the collapse of massive stars, and that's called core collapse supernovae. We don't care about the other type. The type 1A, they are whatever, no one ever wins Nobel Prizes about those. If you have any questions about those vermin, you can ask God. So we're only talking about massive stars that explode. So when I say massive stars, what exactly do I mean? So I mean stars that are more massive than about 8 times the size of the sun. So here's an interesting graph. We're going to assume that we have this sort of mundane stellar nursery. It's going to collapse. It's going to form a handful of stars from its gas and dust. And how is that going to sort out in the mass range? Well, for every roughly 200 and, oh God, I've used both hands? Okay. For every roughly 250 stars that are the same size or smaller than the sun, you only get one really massive star and maybe 1 or 2 stars that are big enough to explode. So to explode, once again, we have to be 8 solar masses or above, so 8 times the mass of the sun or above. So 2 out of roughly 250 we can get that are big enough to explode. Now, to sort of explain this graph here, we just have the stellar mass, and it's in M-sun. So it's so much easier, instead of figuring out how massive the star is in kilograms and grams and T-rexes. Yes?
Are these today's numbers, or what about the early universe?
These are today, and this is a very rough estimate based on all sorts of assumptions, and it doesn't hold, for every galaxy or every part of the Milky Way. It's just sort of an estimate. We do that a lot in astronomy. And so just roughly a sort of normal cloud, you're going to get 1 to 2 maybe massive stars. And there's all sorts of people doing research on, really, is this how it works out, or can you get 5 or 6 massive stars and a lot less small stars? But we're just going to kind of pretend this is sort of the average here. Okay, so once again, we are just worried about these guys here. And to sort of put it in another graphical way, if we put it in a pie chart, 41% of the stars are less than a quarter of a solar mass. Somewhere between half and a quarter, you get 28%. And then as the stars get more massive, you get less and less. If you're going up to between 8 and 20, you get about 0.3% of stars. And this is sort of a mass distribution of stars in our own Milky Way, present day. And more massive than 20, you get about 0.06, so really, really small. Now, so this all boils down to only 1% of stars will end as a core collapse supernovae. Now, fortunately, these stars are really, really, really bright. So they might be few and far between, but they're super bright. And when they go supernova, you can have a supernova explosion that is brighter than the integrated light of the galaxy that it's in. So you might not even be able to detect the galaxy that has a supernova in it in any normal sort of way. Maybe you need a long, long, long exposure just kind of sitting on it to see it. But if a supernova goes off in it, you can say, oh wow, there's an object there, it's bright enough, we can actually see where this galaxy is. But it's not just in the ends of their lives where they are super bright. They're very bright throughout all their lives. And in fact, it sort of works out to where while 1% of stars go as supernovae, the 1% of the stars that do go as supernovae, that are these massive stars, this 1% has 99% of the luminosity of stars. So those numbers may seem very familiar to you if you've been paying attention to any current events in the last couple of years. So 1% of the stars have 99% of the luminosity. So our planet, which goes around the 1 solar mass star, we are all on this planet the 99% in the galaxy, because we only have a star that has 1% of the or less than 1% of the luminosity. Wait, I said that wrong. But anyways, you guys understand what I meant. Okay, so hashtag Occupy the Galaxy. All right, so we get these massive stars that explode. That's the whole point of the talk. So presumably, at some point, I'm going to have to tell you how this happens. So here is a really nice pictorial representation. Oh God, it's so much prettier on my screen. of what happens in the stellar life cycle, okay? So we can all have a common, actually I think I like this better. Can you see it? Yes, all right, cool. We all have a common, so we have a star-forming nebula, and as I was saying earlier, it's not going to condense and only make massive stars or condense and only make, sun-like stars. It's going to make a whole range of masses. So it's going to collapse, and if you're a massive star that has collapsed out of this cloud, then you're going to become just a massive star, 20 solar masses, or 8 solar masses, 20 solar masses, 100 solar masses, maybe 300 solar masses. There have been some claims. And then after some amount of time, you're going to become a red supergiant. Then you're going to have a supernova explosion. And then based on how massive your core is, when you explode, you either become a black hole or a neutron star. And then as you see, the arrow continues, which means that the material that's blown off in the supernova goes back into the interstellar medium, and it's seeds for new clouds, new stars to be formed. And in fact, new Earths, new planets, all of that. Because remember, all of the stuff we need for life comes from supernovae. Now, if you are a sun-like star, you kind of go on a slightly different path, in that you run out of nuclear fuel, and then you just kind of puff off your envelope. You become a red giant, and you kind of puff it off gently, and you become a planetary nebula, and then you just have a little white dwarf left over. But your planetary nebula can return all the material back into the ISM and create stars all over again. So depending on how massive you are, you take generally one of these two paths. Okay, so here is our next trivia question. So you might be able to tell just from this picture, but do you think it takes longer to create a planetary nebula or a supernova?
Supernova.
I heard a planetary nebula right here first. So it does take longer to make a ooh, what's that?
What is it?
It's a chemical poster.
Woo! Oh, that's pretty. Okay. So, I don't know if everyone heard, it takes longer to make a supernova. And in fact, you can look here and see, it's planetary nebula. It takes longer to make a planetary nebula. Maybe I should stop drinking this beer for a minute. And you can just sort of see in the picture that this is kind of a much tighter, smaller circle, and this is much, much bigger. And the reason is that even though massive stars they're more massive, therefore they should have more fuel, they do have a lot more fuel, but they use it a lot faster, and they burn hotter, and they live fast, they die young, and then they explode. So whereas a star like our sun can live for 10 billion years, we're about halfway through. We have a little bit of time left. Because it burns hydrogen and helium, and that's just how it goes for the next few billion years. A massive star, say something that's 20 times the mass of the sun, it's going to only take 10 to 15 million years to burn through all of its material and die. So that's 10 billion versus 10 million, and that's only between a 1 solar mass star and a 20 solar mass star. So the bigger you get, the shorter your lifetime is. And I heard this analogy, I was actually listening to one of Nathan's talks, and that is sort of like if you compare a massive star to like an SUV versus a solar mass star to like a Prius. Yeah, it has a smaller tank, but it can get much further, and that's sort of like the difference between a solar mass star and a 20 solar mass star. Okay, so through the most of its lifetime, how does a star not explode? Okay, well, because it's all of hot gas. Why is it not exploding? Well, there's this constant balance going on in a star between the gravity of the mass of the star pulling it down, trying to make it collapse, and then the radiation pressure pushing up. So you're fusing hydrogen to helium, and you're making heat, you're creating pressure. It's keeping the star, keeping the star supportive, and the gravity's trying to pull back down. So it's a delicate balance, but it does a good job of staying in balance. So let's pretend once again that we have a 20 solar mass star. So remember, 10, 12 million years is how long it's going to live. So for most of its lifetime, so let's say 10, 9-10 million years, it's going to be fusing this hydrogen to helium. So that's what it's going to do its thing. It's going to be massive, it's going to be bright, and it's going to be creating helium. Now eventually it's going to run out of hydrogen to fuse into helium. So what is going to be the next logical step? Well, it's to fuse helium into something else. So we've run out of hydrogen, we should move on to something else. Now when that happens, so it runs out of the hydrogen, we have the helium, the core sort of contracts a little bit, it starts fusing the helium, but it gets really hot. The core gets really hot, and so if we want to keep this sort of equilibrium in check, what do we need to do? Well, if we have a lot of heat, then it's going to make the star expand. It's going to get bigger, okay? So all this heat's making the atmosphere get bigger, but then what happens when something heated kind of expands? Well, it starts to cool off. So even though you're making a lot more energy, you have a lot more hot material in the center of a star, and you're producing more heat, it's going out through the envelope and making it expand and making it get cooler. And it's at this point that you move from that normal blue supergiant, or that normal like bright blue star, into a red supergiant. And you expand. So this is just sort of a normal red supergiant star. If you stuck a red supergiant at the sun's position right now, it would expand out to Jupiter, just the radius of the star. And so you have this red supergiant. Now, all the action is really occurring in the core, which is the very center, 10,000 kilometers or so of this 20 solar mass star. Now, it takes another million years, and we use up all of our helium, and all of a sudden we're out of helium, and we've made a whole bunch of carbon. So what do? We do the exact same thing over again. We sort of contract a little bit, and we start burning carbon, and then we have another maybe 500 years. So each consecutive burning sequence that we go through, we create heavier elements, one, but it takes a lot less time. Okay? And then we go from carbon to neon, maybe that takes a couple of months, and then neon. This is just sort of a rough, there's of course a lot of other byproducts, a lot of other things, but this is, a nice general idea of what's happening inside. So you go from neon and then oxygen, and then maybe after a month or so, you will have only silicon, and then it takes about a day, and you've fused all of your silicon. And yes.
So if you have a neon burning star, can you spot the spectra of it and figure out that it's about to go off?
I can't answer that exactly, but I have a feeling that you would never make it, it wouldn't make it through the photosphere. You would see that you had a really hot, really bright supergiant, but I don't know about the spectra of, you can see the neon in yeah. So you just see the atmosphere, and so.
Too bad, because it'd be really nice to know it's going to go off.
Yes, and keep that in mind towards the end of the talk.
Okay.
We might have a discussion about that. Okay, so you've finally gotten to silicon, and after a day, all of a sudden you have a whole bunch of iron. Okay? So what happens when you have iron? So this is kind of the meat and potatoes of a supernova. This is what happens to make what we see as supernovae. So throughout all of these, so from hydrogen to helium, carbon, neon, oxygen, silicon, you're fusing heavier and heavier elements, but you are creating energy, okay? By the time you get to iron, you have to actually input outside energy to fuse iron into anything heavier, okay? Well, the star doesn't have that. So what's going to happen? Well, the core that is just made of iron can't support itself anymore because there's no reactions going on. It can't keep the radiation pressure up, so gravity wins. And all of a sudden, And by say all of a sudden, I mean like a fraction of a second. The core goes from 10,000 kilometers per 10 kilometers per second. Wow, 10,000 kilometers to 10 kilometers. It goes from this massive core to the city-sized core. Okay, and it's made of iron. And remember now, at this point, the atmosphere is very extended. So, it sort of takes it a hot second to realize, hey, we're not getting any more energy from our core, and then we all fall down. So, we've created a core, like this very super, and we'll discuss why it matters, how massive this core is. This very dense core that can't support itself anymore, that can't fuse anything else, so it's very rigid, and all of a sudden, you've got the rest of your 15, 20 solar masses falling down on you, okay? So this happens in a split second. The outer layers of the stars come falling in, and then it hits the core. And two important things happen. One, which is that the whole atmosphere of the star hits and rebounds. So it was going this way, and all of a sudden it's shooting back out, okay? And then you have all of these atomic particles in the core, and you're hitting it with this, because you're falling in at a fraction of the speed of light. Like you're moving, you're really moving, and you knock out a whole bunch of neutrinos. Okay, and actually, once again, we're gonna go back to our 99%. 99% of the energy in a supernova explosion is neutrinos. Only 1% is the electromagnetic radiation that we see. Okay, so all these neutrinos, which don't normally interact with anything, because they just don't like to, come out through, and it's like kind of like putting a match on a floor full of gasoline. You just light it up. These neutrinos just explosively ignite the atmosphere, and so you have this huge, awesome flash, and it helps push all of the material outwards, and so your expanding supernova ejecta is moving at 10 or 15,000 kilometers per second. So you've just got all the material whooshing out. Yes.
So this is neutrinos normally don't interact with anything. The neutrino flux is high enough that they light up the atmosphere.
Yes, 99% of the explosion energy is neutrinos. So, in fact, and I'll talk about this later on, we did detect 19 neutrinos from a nearby supernova a couple of decades ago. So we can detect them, but they come in such huge amounts from supernovae. That's about the only way we can get a nice flux of them. Yeah.
What's the time difference between when you see neutrinos and then you actually see the light from the supernova?
I think it's a couple of hours. So you'll get a neutrino flux, and then you'll have the light flash. And it leads to the next slide. And this is not quite to the time scale, but here we're going to see kind of a quick animation, and we'll play it first, and then we'll talk through it. All right. So wait, we might not want to go there yet. Okay. So let's explode a star. So that's the core of the star. I promise I'd let you look first. And this is all blue, so you're not missing anything. There's nothing red there. Okay. So this is this is a nice pictorial representation. This is obviously not a real-time video of an event happening, okay? This is just an artist rendition. And what we have is basically, so you have the core collapsing, and then this is the bounce back, and you basically have these neutrinos escaping, but they can also escape as X-rays because they're really heating up that material. Then it cools off, so you get this what we call shock breakout, which is what you saw, and then this expansion is the visible light you would see. Okay, so you go from really, really high energy down to lower energy as you cool and explode. All right, so let's look at another pretty picture. So remember that onion. So we call it an onion skin, an onion layer of the material inside the supernovae. Well, when it explodes, it all has to go somewhere. And this is a really nice composite HST image. And it's done in 3 different narrow filters. So the filters are, so these are images And the filters are optimized to pick out these certain elements. And this one's gonna not be so great. Okay, so red shows hydrogen, green shows sulfur, and blue shows oxygen. But hydrogen is the most abundant, so it's kind of mostly all over there. But this just sort of shows one of our nearby supernova remnants. And they've created a couple of different images and kind of put them together as a fly-through of this supernova remnant here. And we're just going to take a little tour through. It's really not as exciting without the red, but basically there's sort of some filaments there. It's not all symmetric because the explosion can be a little asymmetric. The material that's around it can be a little weird shaped, so you can get mixing. That's all sorts of strange things there. And so not only are you creating heavy elements when you are fusing stuff in the core, but during the supernova explosion itself, you're creating heavy elements. And then you create these seeds of elements that then can start collecting electrons and protons and neutrons from other places and make bigger and bigger elements. And you can also make elements that then decay into smaller ones. So you have all these radioactive processes that are that you can A, detect their elements through imaging and spectra, and B, you can see through different types of observational markers. So one of the interesting radioactive processes that I want to talk about, it's very important for observations in supernovae, is, and this is the third most science-intensive slide of the talk, is nickel 56. So it's nickel, and it's the 56 is the atomic number there. So we just want to look. We have nickel decaying into cobalt. Takes about 9 days. Then you have cobalt decaying into iron, which takes about 111 days. Okay, so why do we really care about this? Well, if you look at the all right, okay. There's a line here, okay, and it goes the slope. I hope most people can see it. Okay, now, so this plot is what we call a light curve, and it's a common tool that observational astronomers use for supernovae. And what we're plotting is days after maximum light. So this is a time scale on the horizontal axis, and the vertical axis is arbitrary numbers, but it's brightness, okay? So once you hit about 150 days, all of a sudden the brightness of this object follows a trend. And it's a very well-known trend. It's the decay of cobalt 56 into iron. We know how bright it's going to be. We know that the light curve itself should follow this at late times, unless there's something really strange going on. So we have a really nice template that tells us, okay, after 150 days, the supernova should just be radioactively decaying, and that's what's powering it, and we should see it get this much fainter over this many days. So it's a really, really useful tool. And it'll come up again in a little bit. Okay, so we've discussed how they explode. Now let's see what they look like in real life when they explode. Okay, so here's a little puzzle. These are 3 different images of the Whirlpool Galaxy taken 3 different time periods. So early 2005, mid-2005, and mid-2011. There's something different in these 2 images that does not exist on the first image. All right, I'll give you a second just to look. And you can see them, they are not red. Okay. Oops, whoops. You don't get to see them. Okay, so, did you guys see those 2? Those different things? All right, so I said this was in early 2005. This is in mid 2005, and all of a sudden, this bright star appeared. Okay, and then it faded, and then 6 years later, we look at the galaxy again, and all of a sudden, hey, this other new guy appears here. So we have 2 supernovae happening within 6 years in the same galaxy. Now, fortunately, M51 is beautiful and it's space on, and we take lots and lots of pictures of it, so we have lots and lots of data of it. Even more fortunately, we have lots of Hubble Space Telescope data of it. And so what people did is they said, oh, we have images of this from high resolution HST images. Let's go and see if we can figure out what star actually exploded. And in fact, in both cases, so this is designated supernova 2005 CS, which meant that it was discovered in 2005 at some point during the year. They start out with A, B, C, then you go to AA, AB. So it was discovered in June, so it's CS. And this is 2011 DH. And that's how we keep up with all of our supernovae. We don't give them these crazy coordinate names. Well, we kind of do now, but that's another story. And we don't give them comet names like based after people who find them. We give them date and then some letters. So in this case, it's a really interesting case where they were actually able to figure out who the progenitors were for these supernovae. And this is really, really, really rare. This doesn't happen. Maybe 15 or 20 cases so far have we sort of figured out or seen directly what the progenitor of a supernova is. Otherwise, we have to kind of go through, use our own supernova forensics, look at the supernova after it has faded some or watch it evolve and figure out maybe what the progenitor was. Okay, so this leads me to what I actually do. One of the things I do here is you can kind of see it. It's called the Arizona Transient Exploration and Characterization, or AZTEC collaboration. So there's a bunch of us at Steward and NOAO who together use telescopes in Arizona to study supernova as they evolve. So, where's the train? I need to chug. Okay. So we use mainly 4 different telescopes. So the MMT on Mount Hopkins, the Bok telescope on Kitt Peak, the Kuiper telescope on Mount Lemmon, and the LBT up on Mount Graham. And we use these to study supernovae from when they're very bright. So that's when we use the smaller telescopes. So the 61-inch and the 90-inch till they're very, very faint. So years after they explode. And that's why we need those giant telescopes there. And so what we do, now we don't discover supernovae, that's not our job. Our job is to let other people do that, and then we follow them up and see how they evolve. And we do cherry pick. We pick things that we think are going to be really interesting, not the run-of-the-mill stuff. That being said, here's a very normal run-of-the-mill supernova that we follow. And this is sort of a quick, this is the second most science-intensive talk, or slide. This is sort of a snapshot of what kind of data we collect and how we use it. So for imaging data, we just get images of the supernova and we just measure how bright it is with time. So we create these light curves, like I mentioned before. In other instruments, we use the spectrograph, which splits the light into various wavelengths, and this is a 2D representation of what that looks like. So this is wavelength along the x-axis, and the y-axis is your space, so it's actual direction. It's an actual distance, and your brightness, your intensity is actually in the z direction, so it's coming towards you. And so what we do is we pull all this data out and we create these we create these spectra that are here, and are also slightly difficult. So this is the spectra of hydrogen. So this is the element hydrogen in a supernova explosion. And this is wavelength here and intensity here. And normally, as a supernova explodes, you get a lot of hydrogen, and you get this really nice sort of bell-shaped curve. But basically, we follow the supernova in spectra with time to see how that changes, because that will give us some very valuable information, which I will discuss in a little bit. Okay, so we are certainly not the first group of people in the Southwest who are observing and recording supernovae. In fact, about 1,000 years ago, there was another group of people that seemed to notice a new visiting star, which was likely bright enough to be seen in the day for a couple of weeks. And here's a pictorial representation. So this is, and I always say it wrong, it's Chaco? Chaco. I am not a native Tucsonian. So Chaco Canyon. So this is a cliff painting there. And it dates from about 1054. And it shows the appearance of this very bright new star near the crescent moon. Okay? So this was backed up. But it's also backed up by other documents from China, Japan, the Middle East that also seem to see this new visiting star. So there is apparently a very bright event in 1054 that was seen on Earth. Okay, now, does anyone know, this is the trickiest one, what we know supernova 1054 as today? Yes, the Crab Nebula, exactly. All right. So the Crab Nebula is not a nebula. It is a supernova remnant. And it is located in Taurus, so it's not even located in Crab, so its whole name is wrong. But it's located near the right horn of Taurus. Okay? And there's a really, besides being a very interesting bright object that's seen on Earth, and that it looks really pretty, and that it's pretty well studied, it has another very interesting thing going on inside of it. Oh my God. Okay, there's red there, but it doesn't necessarily matter for this. Okay, so this is what the Crab Nebula looks like today, in blue. And inside, the very center of it, is a super fast spinning neutron star. So this was a massive star that exploded, and it left a neutron star at its middle. Now this neutron star is spinning, and how do we know that it's spinning? Because it creates a pulsar. So what that means, and I'll show you more in a second, is basically it's like a cosmic lighthouse. It is, as the supernova was exploding, so the supernova was already rotating, okay? Stars rotate just like the Earth. And as it exploded, basically it went from being huge, so that 10,000 kilometers per second, to 10 kilometers per second. So it's like an ice skater. You're spinning around, you move your arms in, you're going to spin faster, right? So when it goes from 10,000 to 10, it's obviously going to get spun up really, really fast. So it's spinning super fast, and it has a strong magnetic field. And the poles of the magnetic field start beaming electromagnetic radiation, okay? So you have a spinny thing with a bright thing on either side, and so you end up getting a lighthouse effect. And this, I meant to say, well, it doesn't matter much now, but this is a very beautiful picture that was taken on the 4-meter telescope here back in 1974. It's gorgeous. And at the same time, they observed this pulsar, okay? So here it is blinking in and out, and in and out. Now, this is very much slowed down because this pulsar is a millisecond pulsar. It has a period of 33 milliseconds. So it does one complete rotation in 33 milliseconds. Okay, so it's really, really spinning around. Now, here's another sort of graphic of what this pulsar, or how you make a pulsar, is you have the spinning neutron star, you have the magnetic field lines here, and then you get your beamed radiation. So if only if it's kind of beamed in our direction can we see it. Otherwise, not so much. Okay, so the Crab Nebula is really interesting and well-studied object in our galaxy. But let's talk about the most, I think, well-studied recent supernova. And it wasn't in our galaxy, but it was in our next door neighbor. So this is a gorgeous photo. You can see most of the things. The Magellan telescope's down in Chile, which Arizona does have time on. You can see the Milky Way galaxy here. And these are our two closest neighbors. And this is the Large Magellanic Cloud and the aptly named Small Magellanic Cloud here. And it's this large Magellanic Cloud back in February of 1987 where a very interesting event happened, and all of a sudden we had a visitor star. A new star was there, okay? So this is previous to explosion, and all of a sudden you had a very bright supernova. Now this is you can only be seen in the southern hemisphere because it's in the Large Magellanic Cloud, which can only be seen from the southern hemisphere. If you haven't had the chance to go to the southern hemisphere, I highly recommend it. The skies there are so much better than ours. They're so lovely down there. They get all the interesting things and the fun parts of the Milky Way. It's just absolutely gorgeous. So this was next door to us. It was, 50 kiloparsecs away, which is just right next door. And because of that, we were able to observe it all the time. So we have the most coverage of a supernova than anything. And we were able to, so in 1987, HST didn't exist. So we couldn't go and look for the progenitor in images. We had to, or in space telescope images, we had to actually use ground-based images, which was fine because it was close by. And there was a really interesting thing. Okay, so we got this great supernova that we could study right next door. That's amazing. Astronomers were thrilled. And then all of a sudden we look at this and we find out that what we believed for a long time is wrong. And that we assume all of these stars explode as red supergiants. Okay, that's all I've talked about is red supergiants. Well, it turns out that the progenitor to 87A was a blue supergiant. So we had to go back and figure out what was going on. Okay, so next question. Which stars are hotter, red or blue supergiants? Blue. I think I heard over here. Yes, blue supergiants are actually hotter. Okay, and I've been discussing all this time red supergiant. So how the hell does this actually happen? And of course it took a while. It took astronomers going through all sorts of models and theory to figure out how this could happen. Well, here's just a very quick image of what astronomers use a lot, where we have the evolution of stars, okay? But basically we have temperature and brightness. And along this line is mass. So you have, it's easier here. Okay, so these are all red down here, by the way. You can't see them. The black things are red. And so red things are cooler, blue things are hotter, and then as you go up this way, you get more massive. And so here's the area we're interested in, and we assumed that supernova stars became red supergiants, and then they exploded. Turns out, during that time when they're making the onion core, they kind of fluctuate back and forth. The atmosphere can expand, and then it starts to fall back in when you don't have as much energy coming out, and so it gets hotter because it's less expand, you go back and forth. So you could actually go back from red to blue to red to blue and bounce back and forth a couple of times and pretty much explode anywhere along this. Whereas the majority do explode as red supergiants, interesting phenomena can happen to let you explode as a blue supergiant. Now, the rest of this doesn't really matter, but the interesting thing to take from this is that, and that I haven't mentioned, is that the whole time these guys are supergiants, they're shedding their atmosphere. And they're doing it, as a red supergiant, they shed their atmosphere very slowly, but it becomes really dense. And then the blue supergiant winds are super, super fast, but they're very tenuous. There's not a lot of material there. So you can imagine as it bounces back and forth, as it goes from a red to a blue, you have these fast winds that are plowing into these slower winds, and it sort of makes it denser and creates various dense rings and shells around these stars, which leads us back to 1987A and this beautiful photo that you guys may or may not have seen, which is the 3 rings. I swear there's 2 more rings you can't see. Around 87A, you have the central ring and then the 2 redder rings that are out here. And these were caused by the supernova going back and forth between red and blue supergiant. And that is actually one of the things that I'm the most interested in, is that we didn't know this existed until it went supernovae, and then the light from the explosion and then the shock as the material moved out heated and lit up all this material, and we could start to see that it was there. Ooh, okay, this should work. And in fact, we have this really awesome time-lapse video from HST images that show this happening. So this is the inner ring here, and the shock of the supernova. So the actual material that I said was moving out at 10 to 15,000 kilometers per second. It slows with time, but as it's moving out, it starts to hit. It starts to hit this material, and you can see the year at the bottom, and after each year, you start to see more things light up as the ejecta runs into it. So between 1994 and 2006, just kind of lights up like a string of lights. And you start to see how clumpy the ejecta is, maybe how the material is dispersed throughout. And this is an ongoing. People are still looking at 87A, and we're trying to figure out, as it becomes a supernova remnant, what sorts of physics is going on there. All right, I'm going to skip the most intensive talk, okay? And we're going to go back to red supergiants. So our final question, all right? What is the closest red supergiant to Earth?
Beetlejuice.
Yes, I heard it back there, Betelgeuse. All right. Yes. So Betelgeuse, which is the armpit of Orion. So here's Orion. There's Betelgeuse up there. It's red. I promise. It's red. It is so here's a nice little, it's roughly the size of Jupiter's orbit. It's about 700-800 light years away, and it's the closest red supergiant to us. So does that mean it's going to be the next thing to go supernova? Maybe. Could be. We don't know. It could happen tomorrow. It could happen in 20,000 years. But this is sort of the most likely normal scenario of a supernova going off next to us. So keep an eye out. That might happen. But more likely, it might be one of these next two stars I'm going to show you. And they're blue supergiants, because now we know they can explode. Now, both of these, the two I'm going to show you, were actually classified, and they both have ring structures. And they were actually found and named by my supervisor at, or this one was found and named by my supervisor at Arizona. So it's SBW1. The S stands for Smith, because Nathan Smith is the guy who wrote the paper on this. And it is a blue supergiant that has interesting ring structures, somewhat similar to 87A. But this guy is only 20,000 light years away, or is 20,000 light years away. So it won't be the closest, but it may be the next one. It might be in the last minute throes of its life. All right, so keep an eye out for that guy. But actually, what seems to be the most likely candidate is this HD. Here, let me show you this. Okay, this is a little easier to see. Is HD 168625. So it's got a very sexy name. And it is a red supergiant that has a ring structure, or it's a blue supergiant. It looks red because this was taken with Spitzer Space Telescope, so infrared, long wavelength of light. But it's actually a blue supergiant, and it has a ring structure that is so similar to 87A. As you can see in this little cartoon, it has a central ring and two outside rings. This guy's about 7,000 light years away, and it kind of looks like this might be our next candidate. And one other thing that I haven't mentioned is that we are well overdue for a supernova in our galaxy. Their core collapse supernovae roughly happen every century. We haven't seen one since the 1700s. So it's been a long time, and we're well overdue. So, keep an eye out. And if you get a news, like some sort of news blip that says, Betelgeuse is going to explode, we're all going to die, no. If it does, it's not going to affect us, and likely we're all going to be dead anyways by the time it does. So with that, I'm going to leave you with this very insightful message, is that we owe our very existence to the stars that explode. So thanks, guys.
Oh, we have plenty of time for questions. I'm sure Jen has some other slides ferreted away that she can also show you.
Well, they're all red.
Never mind.
Okay.
Is it possible, you were talking at the beginning about looking at the light that is coming from these stars and telling what elements are in it currently?
Mm-hmm.
collapse a star is in, and kind of from that guess how long it'll take it to explode?
Yeah, I mean, you can tell. So she was asking, can you take a spectrum and figure out like how close it is to collapse? You can start to see if you have, heavier elemental abundances. You can see if it's gotten brighter but cooler, and you can sort of use that to tell if it's how far along in its evolution it actually is. But no, you can't say, okay, I'm going to take the spectra, you're going to explode in 5.5 million years. I know exactly. I mean, you get an idea that it's an evolved star, but you don't ever know.
What constellation is SPW1?
I don't remember. Maybe it's probably in the south. Odds are it's in the south somewhere in a constellation we wouldn't even recognize.
So let me follow up on that. Can you see that with your naked eye? We all know we can see Betelgeuse with our naked eye, but can you see there are those others?
No, because you maybe can, but once again, I believe if I'm correct, this guy HT 168625 is actually pretty dust enshrouded. So you need an infrared telescope to see it. Now, the SPW1, you could probably see with binoculars at least. So maybe naked eye. So it's bright, but it's 20,000 light years away. So I think it's further away, it looks fainter. I did not do my research on this because, yes. But you can do your research and plug it in and find out if you can see it. So. Yes.
Please excuse my lay ignorance. Is there a period in the development of the universe where supernovae are like a lot more common, less common?
So that's a good question. He asked, is there a period in the universe when supernovae were a lot more common or less common? Well, we first got these heavy elements at the beginning. So we have the Big Bang. We create hydrogen and helium. Okay. Now. We have this sort of theoretical class of population 3 stars, and they were probably much more massive, and they probably only lived a fraction of the amount of time, and so then they created the initial heavy elements that seeded and created other stars. So those were, I wouldn't say more common, but at least you could have bigger ones. The beginning of the universe, and then with time, yes. Mm-hmm.
Thank you.
A follow-up question to that. I love your speech tonight. The graphics are great. Did you just say no supernovas have been observed in the last 300 years within the Milky Way?
So we, as a civilization, as Earthlings, have not detected a supernova since Kepler's.
Oh,
yes.
That blows my mind. Thank
yes, but that doesn't mean that one hasn't happened, right? It just means we haven't seen it. So remember, we're out on this very sort of, lonely neighborhood out on a spiral arm of the galaxy, and if a supernova happened on the other side, we might not be able to see it because there's so much gas and dust in the center of the galaxy that it would never make it to us. So that doesn't mean that one hasn't happened, it just means that we haven't detected it. But if something did happen that wasn't completely obscured by gas and dust, we would see it, we would know. And the interesting thing is, the first people who are going to know are amateur astronomers. Because they spend their time every night out looking through their telescopes and looking. They know galaxies like the back of their hand. They can look through their telescope at a galaxy and say, that star is not supposed to be there. And they will likely be the first line of defense to tell us when a supernova has gone off in the galaxy, because they just know. And it's probably going to be this one guy who discovers everything down in Australia. So, yeah.
You drink a lot there.
Yeah. So it might not be real, but, Yeah, right here.
What happens to objects that are orbiting a star once it goes supernova? And I guess, how does the gravity affect objects that are maybe further out?
Right. So you have a lot of mass in one space, and then all of a sudden you have less mass, or you have the same amount of mass, but it's in a much wider area. So it's obviously going to destroy anything in its way that is, super close, and any sort of orbital dynamics, all of a sudden you are left with, a 2 or 3 solar mass core, not the 20 solar mass thing before. So whatever happens, it's not going to be good. So that's a very quick and dirty answer on that. All right. Yeah?
Oh, you mentioned that like you end up, you had 20 solar masses and then you go to 3 solar, so that's 17 solar masses that can convert it to energy?
No, because yes and no, in that a lot of this mass is lost during the wind phase. It sort of depends on how much mass loss you get. But yes, and it's not necessarily as much energy. You also, all this material just flung out into space. Yeah. You have another one? Yes.
Are there components of any of the new telescopes, I think it's the James Webb, that,
Mhm.
that are particularly directed at supernovae?
I don't know if they're particularly directed, but because it's going to be sensitive to the more, what? Oh yes. So I'll get to that in one second. Okay. So James Webb will be really good to look at these guys that are hidden behind a lot of dust. It'll be able to allow us to see supernovae further away, because as you go out distance, things get red shifted. So bright supernova would be shifted into wavelengths that are more easily seen with infrared telescopes. So we'll get to see supernova further away. Now, if we want to find a lot of supernovae, we have this amazing thing called the LSST, the Large Synoptic Survey Telescope that Arizona is involved in. And it will be a survey of the sky that will find tons and tons of transient objects and tons of supernovae. And I imagine if you're really interested in that, there are a lot of talks and public talks around where you can learn about that.
Thank you.
Yes. All right, maybe one more. All right.
You had mentioned the detecting like 1920 neutrinos and that neutrinos detected about an hour before the light shows up. Can you use those neutrino detections to pinpoint where to look to see the light?
So you can't pinpoint because because you're getting bombarded on Earth with neutrinos. So you can't use a neutrino detector you can use it to predict an event, but you can't use it to say where the event is going to be. So you just have to wait for the light to show up. And in fact, they didn't use that in 87A. After the supernova went off, then they said, oh yeah, we had this burst, and it was correlated with that event. Yeah. But if you have that many coming through, then they'll know there must be something nearby that's doing that. Yeah.
Speaker needs to have the rest of her beer, but let's thank her again. So that actually brings us to the end of a whole year of Spacecraft again. This is December, so we'll pick up again in January, where we'll have our first speaker from out of town. Now, Rachel is the runner of, or the organizer of Astronomy on Tap in Texas. So this is actually what you're attending over here is not just a local Tucson thing. It's actually nationwide. You're really part of a big movement to get astronomy out of like classrooms and labs and into the public and get you guys interested about this stuff. And so our talk next semester will be January 27th or 28th. I'll put it up on Facebook if you follow us and on Twitter or whatever else. And we'll be talking about the HST frontier fields. These are massive fields that are surveyed by HST with large galaxy clusters, and they're strongly lensed. We have a researcher down here from UT Austin who will be telling us about her work on this stuff. So it should be really interesting, and it will be a really cool test of general relativity just after its 100-year anniversary. So join us again in January and watch out for this event, and thank you all again for coming back.